Hi everyone, and welcome to Lesson 4 of the PLC, Programming Full Course. In this lesson, I'd like to introduce a more professional way to learn PLC programming by working on real-world practical projects. Starting from this lesson, each video will focus on a practical project. These hands-on examples will help you see how PLC programming is used in real industrial applications. In this lesson, we'll start with a simple and practical project. Controlling an electric motor using a PLC and a contactor. Project objective. When I press the start button, the contactor is energized and the motor starts running. When I press the stop button, the motor stops. For this project, I'll be using a CPU 312C, which will be used throughout the course. I've also prepared the following components: 2 push buttons, start and stop, 1 relay and 1 contactor, 1 electric motor. Before we start programming, let's do a quick review of what we covered in the previous lesson. In Lesson 3, we learned that to program an S7-300 PLC, we use the SIMATIC Manager software. The first steps include creating a new project, performing hardware configuration, and then starting the programming. I'm quickly going over those steps again, so new viewers can follow along without confusion. First, I'm creating a new project in SIMATIC Manager. Then, I'm inserting a SIMATIC 300 station. Next, I'm opening the hardware configuration. In this step, we're defining and configuring our hardware. Now, I'm adding a rack by opening the SIMATIC 300 folder and selecting the rack. Then, I'm inserting the CPU. In my real hardware setup, I'm using a CPU 312 compact. Since this CPU is compact and already includes enough inputs and outputs for this project, I'm not adding any extra modules. Now, I'm checking the input and output addresses that I'll use in the program. As you can see, the default address for inputs and outputs starts from 124. I changed this address to 0, but you can leave this field unchanged, as long as you use the same address in the program. Once everything is set, I'm clicking on Save and Compile to complete the hardware configuration. Now everything is ready for programming. I'm opening the OB1 block, and from here, we're starting to write the program. The OB1 block is the main program block in the S7-300 PLC. When the PLC is in the run mode, it continuously executes the OB1 program cycle in just a few milliseconds. This is just a quick review to keep the video concise. If you need a more detailed explanation or run into any issues, please go back and watch Lesson 3, where everything is explained step by step. Now, let's jump into the programming. To control the motor in this project, we need to understand bit logic instructions. These instructions work with only 2 states, 0 off and 1 on, just like real-world devices such as push buttons and contactors, which can either be activated or deactivated. Bit logic instructions are based on the binary system, which includes only 2 digits, 1 and 0, in the world of contacts and coils. 1 means the component is activated on or energized. 0 means the component is not activated off or de-energized. If I open the bit logic folder, you can see several instructions, each serving a specific function. To use them effectively, we first need to understand how they work. First, let's start with the normally open NO contact. By default, the normally open contact is open, so the logic flow is blocked. Result is 0. When the assigned address becomes true or active, the contact closes, and the logic continues. Result is 1. To use this instruction, we need to assign an address to it. This address can be an input I, represents physical input signals, such as push buttons or sensors. An output Q represents physical output signals, such as relays or motors. A memory bit M, used for internal, on-off states within the PLC. A timer T allows activation based on a timing condition. A counter C activates when a predefined count is reached. This means that the normally open contact is not limited to just input addresses. For example, I can assign a timer to this contact. When the timer is activated, the contact will also activate, allowing the circuit logic to proceed accordingly. The same applies to memory bits. Let's take a closer look at this circuit. In this setup, I have used 3 inputs. Imagine that, in real hardware, these inputs are connected to 3 normally open push buttons. In this circuit, 2 of these instructions are connected in series, and then they are connected in parallel with the third one. To activate the output, I have 2 options. Press both push buttons connected to I0.1 and I0.2 at the same time. Press the single push button connected to I0.3. Either of these conditions will complete the circuit and activate the output. Let's take a closer look at series and parallel connections in PLC programming. These fundamental concepts play a crucial role in designing efficient and reliable PLC programs. Mastering them will help you build better automation systems and improve your control logic in real-world industrial applications. Series connections. In a series connection, multiple contacts are connected in a single path. This means all the conditions must be true at the same time for the output to activate. Take a look at this ladder diagram. Here, we have 2 normally open contacts connected in series. If I0.1 and I0.2 are both off, the circuit is incomplete, and the output remains off. But as soon as both inputs are activated simultaneously, the circuit is completed. Current can flow, and the output turns on. This is called a series connection. Where are series connections used? Series connections are commonly used in safety and control systems. For example, in a hydraulic press, operators may be required to press 2 push buttons at the same time using both hands to start the machine. This ensures their hands are away from dangerous parts and prevents accidental activation. Parallel connections. Now let's move on to parallel connections. In a parallel circuit, multiple contacts are connected side by side, so only one condition needs to be true for the output to activate. Here's a ladder logic example. In this circuit, we have 2 normally open NO contacts, I0.2 and I0.3, connected in parallel. If either I0.2 or I0.3 is activated, the output turns on. Each contact provides an independent path for current to flow, so the logic is more flexible. Where are parallel connections used? Parallel connections are useful when we need to control a machine from multiple locations. For example, if we want to start a motor from two different control panels, we can connect two push buttons in parallel. This allows the motor to start when either button is pressed. Key differences between series and parallel connections. In series connections, all inputs must be on for the output to activate. In parallel connections, only one input needs to be on for the output to activate. Both connection types serve specific purposes in automation, helping you design flexible, safe, and reliable PLC programs. The second bit logic instruction we'll explore is the normally closed NC contact. Unlike a normally open contact, a normally closed contact is active closed by default, which means it initially produces a logic 1. However, when the assigned address becomes active goes high, the contact opens, breaking the circuit and producing a logic 0. Just like normally open contacts, normally closed contacts can be assigned to different types of addresses. Inputs I represent external devices like push buttons or sensors. Outputs Q control devices like relays or motors. Memory bits M used for internal on-off states. Timers T used for time-based control. Counters C used for count-based logic. Let's examine this latter logic example. I0.1 and I0.2 are connected in series, meaning both must be on to complete the circuit. These two series contacts are connected in parallel with a normally closed contact I0.3. In its default state, I0.3 is closed, allowing current to pass, so the output is on. But when I press the push button connected to I0.3, its address becomes active. The contact opens, breaking the circuit, and the output turns off. In this circuit, we have two ways to activate the output. Let I0.3 remain in its default state not pressed, so the circuit stays energized. If I press both I0.1 and I0.2 simultaneously, they complete the series path, activating the output even if I0.3 is pressed. Where are NC contacts used? The normally closed contact is widely used in safety circuits, interlocks, emergency stop functions. It ensures that certain safety conditions are met before a machine can operate, making it essential for fail-safe control in industrial automation. Output coil instruction. The third bit logic instruction is the output coil. It's one of the most essential instructions in PLC programming, used to control physical devices like motors, relays, lamps, and solenoids. It operates based on a simple logic. If the preceding logic conditions in the ladder diagram are true logic, 1, the coil is activated turns on. If the conditions are false logic 0, the coil is deactivated turns off. Assigning an address to the output coil. The output coil is usually assigned to outputs Q to control physical devices like motors, indicator lights, or valves. Memory bits M for internal logic or to hold on-off states within the PLC. Example: we have a relay connected to Q0.0. When this address is activated in the program, The PLC energizes the corresponding output, turning on the device, for example, a motor. When the logic goes false, Q0.0 deactivates, the relay is de-energized, and the motor turns off. Here's a simple example. Two normally open contacts, I0.1 and I0.2, are connected in series. At the end of this rung is an output coil at address Q0.0. If both inputs are on, the circuit is complete, and Q0.0 is energized, turning on the connected output device like a lamp or motor. If either I0.1 or I0.2 is off, the logic breaks, the coil deactivates, and the output turns off. Why use the output coil? The first two instructions, normally open and normally closed contacts, are used to evaluate input conditions. But to control output devices, we use the output coil. Set S coil instruction. Now that we've covered the standard output coil, let's move on to an important instruction, the Set S coil. This instruction is used to latch outputs or memory bits, meaning that once activated, the output stays on even after the input condition changes. The set coil can be assigned to outputs Q, used for controlling physical devices like motors, solenoids, or alarms. Memory bits M, used to store internal logic states within the PLC. How the set coil works. The set coil turns an output on and keeps it on until it is explicitly turned off by a reset coil R. When the input condition associated with the set coil is activated logic, the assigned output turns on. The output stays on, even if the input condition later changes, turns off. The output will remain latched on until a reset coil instruction explicitly deactivates it. Let's assign a set coil to Q0.0, representing a device like a motor or a light, and connect it to a start button at I0.1. When I0.1 start button is pressed, Q0.0 turns on. Even if the start button is released, Q0.0 stays on because the set coil latches the output. The output remains latched on until it is turned off by a reset coil R. The set coil S is typically used to maintain a state in situations like holding a motor on until a condition is met to turn it off. It ensures the output stays on without needing the input to remain activated. Reset coil R instruction. When we use the set coil S to turn on an output or memory bit, we need a way to turn it off when necessary. That's where the reset coil R comes in. It is used to turn an output off and keep it off until it is explicitly turned on by a set coil S. The reset coil can be assigned to outputs Q, used for controlling physical devices like motors, solenoids, or alarms. Memory bits M, used to store internal logic states within the PLC. Let's imagine we have an output with the address Q0.0 that is turned on using a set coil S. Now, to turn it off, we use the reset coil R. When the normally open input I0.2 is activated logic 1, the reset coil R is triggered, and the assigned output Q0.0 turns off. The output remains off even if the input condition changes, turns off. The output stays latched off until a set coil S instruction explicitly reactivates it. After completing the program, you'll see how simple and practical this project really is. In the real hardware setup, the Start Push button is connected to input I0.0. The Stop Push button is connected to input I0.1. The motor output via a contactor is connected to output Q0.0. We've now learned the necessary bit logic instructions for today's project. Let's move to the OB1 block and start writing the program to control the electric motor using the Start and Stop buttons. First, I'm writing the program to start the motor. To do this, I'll insert a normally open contact in network 1. I simply click on the normally open contact in the instruction list to add it. You'll see a red question mark appear above the contact. This means I need to assign an address. Since this is an input device, I'll use the I prefix. I connected the Start Push button to I0.0, so I enter I0.0 as the address. Next, I insert a Set Coil S instruction to activate the output when the Start button is pressed. This will ensure the output stays on, even after the button is released. The output address is Q0.0. I use the Q prefix to identify it as an output. Now, Q0.0 is linked to the coil. Let's quickly analyze this network. When the Start button I0.0 is pressed, the No Contact is activated and becomes True Logic 1. This triggers the set coil, turning on Q0.0. The output Q0.0 remains on even after the Start button is released, because the set instruction keeps it latched. Now, let's move on to the Stop function. To organize my program, I will add a new network. To do this, I will select the New Network option from the toolbar, or you can press Ctrl+R simultaneously. In Network 2, I insert a normally closed contact. This represents the Stop button. In my real hardware, I've used a normally closed push button connected to I0.1. So, I assign I0.1 to this contact. You might ask, why use a normally closed button when we could use a normally open one? Using a normally closed Stop button adds a layer of safety. If I were to use a normally open button and the cable between the button and the PLC got disconnected, the PLC wouldn't detect any signal, so pressing the Stop button wouldn't stop the motor. That could be dangerous. However, with a normally closed button, if the cable gets disconnected, the signal to the PLC becomes false zero, and the PLC assumes the Stop button has been pressed, turning the motor off immediately. It acts as a fail-safe. This is why normally closed buttons are commonly used for stop and emergency stop functions in industrial systems. Finally, I add a Reset Coil R instruction and assign it the same output address Q0.0. This ensures that when the Stop button is pressed or disconnected, the motor output turns off and stays off until the Start button is pressed again. Now that we've finished writing the program to control the motor, you can see that it's actually quite simple. Next, we need to download this program to the PLC. To do this, you'll need a PC adapter, which serves as an interface between the computer and the PLC. Connect one side of the adapter to your laptop's USB port and the other side to the MPI port on the PLC, as shown here. When the adapter's LED indicators light up correctly, it means the connection is successful. Before downloading, make sure the PLC is in stop mode. First, we download the hardware configuration. Go to the Hardware Configuration page. Then click the Download option from the toolbar. In the dialog that appears, click OK. In this window, first click on View to display the CPU, then press OK to proceed to send the configuration to the PLC. After that, go to the OB1 block and download the program by clicking the Download button from the toolbar. Now the program is successfully downloaded to the PLC. Let's test it. Put the PLC into run mode. When I press the Start button, the PLC sends a signal to the output, which energizes the contactor, and as a result, the motor starts running. When I press the Stop button, the PLC deactivates the output, the contactor turns off, and the motor stops. Important note about wiring. In my setup, the PLC outputs are 24-volt DC, but the contactor coil requires 220-volt AC. That means I cannot connect the contactor directly to the PLC output. Instead, I use an intermediate relay. The relay connects to the PLC output. The contactor coil is then connected to the relay. When the relay is energized by the PLC, it activates the contactor, which in turn starts the motor. Even if your PLC output supports 220-volt AC, I still recommend using a relay between the PLC and the contactor. This adds an extra layer of protection if the contactor malfunctions. The relay helps protect the PLC from damage. That's the end of this video. I hope it was helpful and that you enjoyed it. If you did, please don't forget to like the video and leave a comment to motivate me to create more content. I'll see you again soon with another practical and useful video. Take care!